Hello, everyone. My name is Markus Gerber. I'm marketing manager at Invent in our section DNS, which is Data Center Networking Solutions. Welcome to this session. I would like to talk today a little bit about how we protect infrastructure, IT asset, network equipment in a changing environment. First of all, when you walk around the halls, you will probably see a lot of these words: cloud computing, multi-cloud computing, hybrid cloud computing, fog computing. All this probably more in the software area, but all around it's also edge computing, deep edge computing, or even deeper edge computing. And I would raise the question if these technologies or these new trends are really game changing for the IT infrastructure. And my answer, my opinion to that question is, it depends. I would say yes to some new technologies, and I would say no, because the buzzwords are just used to replace what we want to rename what we already did over the last couple of years. And will the infrastructure change tomorrow? I would say no. And the good example here is maybe OCP. When you think back a couple of years, even now, everyone was talking about OCP. OCP is still important. It's not gone. I'm a big fan of the OCP idea and the infrastructure, but have it really replaced the way we are working? No. And what have not changed is two main criteria, which is uptime and the right balance in between invest and operational costs. And I strongly believe this is the two main drivers when you think about any IT infrastructure, when you think about any communication infrastructure. The data needs to be available, and when you set up your infrastructure, you have to validate which is the best invest for the best solution, because the infrastructure will run for a couple of years, and then you must have a look at the operational costs. So what is the first thing when we look at these two topics that come to my mind is management, infrastructure management. You have this fancy little graphic here. It's an eye chart. I have to apologize, but you can probably stop and zoom in here. So what I try to capture is the landscape. We're gonna have more decentralized installations, that's for sure, because there are applications which demand shorter latency and demand processing data closer to the end user, closer to the source where it's needed. And therefore you have to consider, okay, do I have the right management gateway to provide environmental data, but also data of cooling solutions? Is the pump working? Is the temperature, the humidity level on right? Into a central monitoring software and process and analyze decentral data at a central point. The same thing is on high performance computing, for example. When the packing density in a rack is increasing, you have more heat on a smaller footprint, you have new cooling solutions, and this clearly drives the demand for data monitoring and data management, so that you are not just able to have a preventive maintenance, but also being able to monitor what is going on and to act instead of just reacting in case of any alert or failure. The next topic and the next thing that comes to my mind is for sure cooling. And we put together this nice chart where you can see edge computing, in that case more for renaming decentral installations, and then the data center floor space cooling. And I would say there is a mix of traditional ways of cooling, and there is also coming up new innovative ways of data center cooling. And just staying a little bit on the edge. And now I'm coming back to the buzzword. Is it changing the infrastructure? No. And one good example here would definitely be a networking rack in an industrial environment that maybe today hosts an IoT server with a very, very low heat. And this means we are talking about installation, networking installation that we have done for several years. And this installation probably go up to 2 kW heat load, and you can handle that with convection cooling, meaning you don't even have an air conditioner cooling device installed in the cabinet. It's enough to just have the heat in the rack, and then over the side panels or the top cover of the rack, the heat is transferred in the room, and even the room will not really heat up. The next step, if you want to add some filter fans or fans, this can be helpful. And then moving up the chains, there will be installation with a little bit higher heat load and application driving this. And then, but you can still use proven technology, which is air conditioners. And there is a few applications, and I would say that's a change. But the application is driving us here. And a very good example is probably autonomous driving. Here, you have to analyze data in real time. And even it's not 100% decided yet how this infrastructure will look like, but most likely you will have more computing power closer to allow this autonomous driving, to allow this technology. And therefore you have to think of how can I cool this computing power. And there easily it can go up to 10, 15 kW per rack. And to be efficient, you should consider some active heat exchanger, maybe moving away from refrigerant and DX cooling towards a liquid cooling solution, whether as a side cooler in rack or as a 19-inch rack mount unit in the cabinet, just to address the needs of these new applications. What I would like to talk now is, because this is an area where we can still save a lot of energy, and this is the data center floor space. Even having all these edge installations, we won't get rid of our backbone data centers. There is two technologies, which is the air containment and in-row cooling, which have been widely adopted on the market. I would say that's state of the art. So, and it makes sense. So if you can limit your heat load to a certain point, air containment separating cold and warm air definitely makes sense. If you increase slightly the heat load, then in-row cooling in combination with air containment makes sense. But if you go down the chain and you say, hey, the heat load reaches a certain point, which is 20, 25 kW, and even with lower heat loads, you can consider that, by the way, then you can move towards a rear door cooling solution, or thinking about for high performance computing applications, even for direct to chip cooling. What is going on here, especially when you look at this chart right to left, we are moving, and that's a trend, we are moving away from room to raw to rack to equipment level of cooling. So we are moving really closer to where the heat is coming from. And I think that's the only way, or that's an important way of getting efficient, high performance computing in place and having the right thermal management in place. Now we talked a little bit about liquid cooling, and there is ASHRAE that came up with some new ideas and bring in some glasses. Frankly speaking, I would break it down to the main idea. The higher the water inlet, or the higher the liquid inlet temperature, the better. What does that mean? This means you need less energy upfront to cool down the water. So every degree that you can increase the inlet temperature of your liquid, the more energy you save upfront. And that's the main idea behind all these documents. Keep that in mind. We come back to that. And now we talked moving away from the raw toward how does such rear door cooling, how does such rear door works? Yes, I'm a marketing guy, so I put in 55 kW per rack. That's really the high end, but it's possible. What we do, or what the cooling solution is doing, you put a coil on the rear side of the rack, which replaces the rear door. And in this coil, a liquid flows. The heat is transferred from the fans of the equipment, is pushed through this register. The heat is transferred to the liquid circuit and is taken away. So the air is cooled down when entering the room. This means you have the same stable level of temperature in the room. And moving closer to the heat, this already allows higher liquid inlet temperatures, which reduces your operational costs. And even with a rack-based cooling solution, if you have all your racks equipped with these doors, in case of any failure, the other ones is taking over. So the room is not really heating up and the equipment is taking the air from the room. Let's go a little bit more in details on the regulations. It's basically very simple. So how these systems operate is you have a set point and then you regulate against the set point. In this case, there is a water circuit, the liquid circuit, and then you choose which is the temperature I want to have on a stable level. So you can pick, for example, the room temperature at 22 degrees Celsius, and then the water flow is adjusted to keep exactly this temperature in your room. And now coming back to my example, so if one of the doors would fail, the room would not heat up because the other ones, they regulate on this 22 degrees. So they will take over and your equipment, there is no risk or very, very small risk that your equipment is overheating. What can happen is, because the air have to be moved by the equipment, that there is an air resistance with the coil. To overcome this air resistance, you can add fans on the rear side, and then we suggest to regulate these fans not by temperature, but regulate these fans by differential pressure. So take the pressure difference inside the rack and outside the room, and if it's becoming too high, then adjust your fan speed accordingly and support the IT equipment. The next step is going directly to the chip, so bringing liquid to the chip. There is also some discussion points or facts listed on this chart, but how does it work? So it's a cold plate. It's mounted directly on the CPU inside the server, and the liquid is circulating around this cold plate and is taking away the heat. Why should I do this? The advantage is you can increase your cooling capacity by having this solution, because the service is getting more and more powerful. You will not have only one CPU, you will have several CPUs inside, and you can really increase the capacity. And if you think the temperature inside the equipment is much higher, so the liquid inlet temperature needed to cool a server is higher than in a traditional room layout. And this allows you, of course, also to reduce your operational costs. So now you would probably ask the question, if I can use higher temperatures, if the stuff is available, how does it build up? I see three modules. The first module is the server. Already mentioned, there is a cold plate on the server. And as of today, the main server manufacturer already offer different type of servers with a pre-installed cold plate. And then this server is connected to a rack manifold on the rear side. And this works basically like a PDU. and then it transfers liquid to the different servers. And the last component you need is the so-called CDU, coolant distribution unit. And inside this cooling distribution unit, you have a pump or redundant pumps that pump the liquid through the manifold, through the server, and let it circulate, taking away the heat, to a liquid-to-liquid heat exchanger that is integrated in the CDU, where you then transfer away the heat from the server to the facility pipework. These CDUs, as of today, can be like a rack mount 19-inch CDU in the bottom of a rack, or you say, no, I have a system of 2, 3, or 4, or even more racks that I want to support with one unit. Then you can use a standalone CDU just besides the rack, supporting the infrastructure. Now you could say, okay, highest cooling capacity, servers are available, I don't have to care about warranty, I can drive with very, very high water inlet temperatures. So why not everyone is moving towards direct-to-chip cooling? And the main reason is, can it really replace air as a cooling medium? And probably the answer is, and you guess you know it, is no. Building up a cold plate that would cool every component inside a server will be very complex. And then we go back to the very, very first point, which is invest and compared to operational costs. So from an invest side, it would not make sense. So what is happening is the cold plate is mounted on the components which produce the most heat, and all the other components around have still to be cooled by air. And this is just an idea how this could work. You can combine different cooling solutions and take the best or the most benefits out of these solutions, building up a hybrid cooling solution. In that case, we talked about the rear door, and we combine it with a rack mount CDU. Let me get you a layout. So on the layout, we said there is an air loop. The air loop is used to cool components which are not direct-to-chip cooled. And there is still air moving from the front to the rear. And you can decide whether the equipment need fans or not. So you choose a rear door on the rear side of the rack. And then you have the primary side. This is the facility side. You connect the door to the facility. This means your chilled water is coming to the door. And over this circuit, you cool the air circuit. Then you have a return liquid temperature. And this return temperature goes to the CDU. Because, as mentioned before, on the cold plate on the server level, you don't need really low temperatures on the liquid side. So this return temperature is enough to cool the server side. And then what you achieve is you achieve a higher delta T on your facility side, and that helps getting efficient. Now I hope this was clear. If not, what we did is we just put in some examples. So operational point 1, 15 degrees Celsius on the facility side on the water circuit. We say we want to get 22.5 degrees Celsius on the air side, 35 air side return temperature. And then we support the liquid to liquid heat exchanger in the CDU. And we get the return temperature to the facility of 36.9 degrees. Makes sense so far? I would say yes. But you could raise the question, 15 degrees on the facility side, on the water circuit. All crack units, they can work in the meantime with 18 degrees or even higher. So where is the benefit of energy saving, building up the system in that way? So let's go at the end of the raw, which is the operating point 4, 40 degrees. Inlet temperature on the water side. Of course, your air circuit cannot be colder than the cooling medium inlet that you are using. So 41% on the air side, which allows almost 50 degrees return to the facility. Now I'm not in the room, but I will probably see some of you shaking your heads or say, okay, what he's telling us right now. For sure, this is the end of the raw, and I would guess the truth is somewhere in the middle. So if we are looking at this chart, you see the different operating points, 1, 2, 3, and 4. And let us have a look at operating point 2, which says facility supply side 20 degrees, room temperature 25 degrees. Makes sense. In that case, we can achieve 86 kW cooling performance by combining the rear door and the rack CDU, while 20% of the components is air-cooled and 80% is direct-to-chip cooled, which is almost the ratio that we have inside the server equipment. When you now move up a little bit the chain to operating point 3, you will see, okay, what is happening if my supply water temperature is at 30 degrees? Of course, you have to accept the higher room temperature. The cooling performance of the rear door is going slightly down. So therefore, the overall performance of the combined system is going down to 63, which is still a lot. The percentage on air and liquid is still in the raw, and you could say, okay, this is something I can consider. While I would say the roof or the best operating point always depends your location and the equipment you are using, but take these operating points as examples. And I believe this is a very efficient way or a very good way of cooling high performance computing applications in the future. And of course, you can always combine different solutions with each other. And that's also our approach to get the best fitting solution for you. So I'm at the end of my presentation. If you are interested, not just in cooling or monitoring, if you have a demand for heat tracing, leak detection, or you simply look for a very good enclosure for your IT assets, then you are right at Invent. Thank you for your attention. And here on the right-hand side is my email address. So in case you have any questions or you want to discuss any point further, feel free to reach out. Send me an email. Now you got my name. You will always also find me on LinkedIn. And I'm happy for good follow-up discussions, feedback, and even critical discussions. So thank you for your attention. And yes, I hope to see all of you soon in person.